I'm going to show how to do image analysis of a microCT image of a porous media. Here is a sandstone. So I'm going to show how to create a region of interest in ROI for the pore space. Then we crop the ROI by a cylinder. Then we calculate the total volume fraction of the pores. Then we use the Dragonfly software's bone analysis tool. Well, it's a module for it's an extension or module for bone analysis, but it has tools which can also be used for other subjects. So we are going to use this tool for generating the dispersion of volume fraction in 3D. So this is Dragonfly, and I have loaded the data. This is a microCT image of a sandstone, and this is where I downloaded the data. So you can go to Digital Rocks portal. It's a project 172. So you can download this. It's a dry scan of that sample. To create a region of interest, we go to segment, we create a new one. The new ROI, the geometry will be based on the image. Now we have only one, so it's a default setting, and we give it a name. Oops. Check my language. Okay, so this is the pore space. And I'm going to create an ROI, and here the Dragonfly also has multi-ROI, which will have multiple classes, but at this moment we just need a binary region of interest, so it's an ROI. After this created, it's new, it's empty, so you don't have any labeled voxels in this ROI. Now the second step I'm going to do is to use the range tool. Here, when I check the define range, I can choose what range, also by histogram, which range of the voxels, the voxel intensities that I want to have to include to my ROI. Now it's the pore space, so I can change the bars of the range. So now the color tells me which pixels or voxels have the intensity in this range, this selected range. The range can also be input by the numbers here. So I change my upper level, my upper bar, so I get visually I need to verify if this range is a good one to represent my pore space. If it is, we just add. This add button will add all pixels, or essentially it will label all pixels to my ROI. So this is a binary labeling, binary ROI. So now I have all the pixels labeled if the pixel has intensity in the range. So this is the threshold-based segmentation. It's very quick, but it may work with some dataset which has a good range for arrange differences between faces, between two or more different faces, but it may not work everywhere. For example, you have some pore space which has maybe higher intensity than the other pore space, so the single range or threshold may not work everywhere, or if your image have some intensity non-uniformity, or some, for example, that beam hardening effect. So the single threshold may not work for the whole dataset. In that case, you need some advanced tools like deep learning, like watershed, or other advanced tools to create the ROI. But for this sample, we got a pretty good segmentation for the pores. Now we need to crop it because like near to the edge and the outer space, the air, so they are not the real pores that we want to we want to do the analysis. So I'm going to add, in the main tab, I go to the shape tool, the shapes panel. We have quite a few shapes here. I'm going to use the cylinder. So I click the cylinder, you will see this is a multiple views of from different directions or different planes. So you will see the cylinder now, and I can move the face of the cylinder either in 3D or in the 2D views. Okay, I can also move the cylinder here or here. So this shape tool can have a few actions, like it can remove it can be like the region of this shape. It can be either removed from an ROI or an image. So we say we see structured grid. The structured grid may be an ROI or maybe an image data set. So now it can also be used to extract or to mask. Now we are going to use the mask menu, and we choose a structured grid, which is the pole space. Now we see the ROI, the pore space ROI has been cropped by the shape, the cylinder shape. I can make it more highlight. And to get the volume fraction, the total volume fraction of the pore space, we need to also have the total volume of this cylinder area. So we are going to create another ROI. So let's say total volume. Then we can add two ROI, which means we add the cylinder area to the ROI we just created, which is the total volume. So total volume. Now we have two ROIs. One is for pores, one is for the same area, but it's a total. It's every pixel is labeled. So when we select the total volume, we go down here, we see compare with. So you can compare one ROI with another one. So if we compare the total volume to pore space, then we do refresh. We got a number here is 15%, 15.17%, which is the total volume fraction of the pore space. It's a volume of the pores divided by the volume of the total area. Now we are going to get the dispersion of the volume fraction. Because the total volume fraction, it doesn't tell you how the pore space is distributed. So is it the same? It's the same volume fraction everywhere, or is it somewhere we have big pores, which is like more the pore space is more concentrated in some locations. So the dispersion will tell us how uniform the pore space is distributed. So we're going to use the tool in bone analysis in Dragonfly. For sure, now we don't have a bone, but we can use the tool in bone analysis to do the dispersion. I'm going to select the pore analysis, the pore space RY, and the image by pressing the Control key. So I multi-select both, then I right-click and say, and we see the bone analysis wizard. So we click bone analysis wizard. This is a wizard for doing the bone analysis. There's a lot of things about the bones. For example, the bone segmentation and thinning. This one we don't really need, so I just skip this step. So go to the next one. Also, the second step is for the second step in the wizard is for separating the bones, the cortical and trabecular bones. For sure, it's not used for our project now, so I just skip it again. And this is for calculating the measurement of the bones. This is now used, so I skip to the step 4, and this is the tool we can use. Step 4 is to do the scalar value and the vector field. We could do the volume fraction or the anisotropy. Anisotropy has two algorithms. One is Mill, one is surface normal. So we don't talk about that for now. So we just go to volume fraction. And this is the bone ROI. For now, it's the ROI of the pore space. So we choose the pore space. This wizard is designed to do the bone volume fraction, like how much bone tissue versus the total volume. Now the pore space ROI is being used as the bone for calculating the volume fraction. So I just choose the pore space ROI, and this is a sampling of the map, the dispersion map. Just the original image might have, we can see it here, it has like 600 pixels wide and almost 600 pixels high and 1300 pixels deep. We could do a mapping which is which doesn't have to have the same pixel size as the original image data. So I can choose for the mapping which is the spacing. I could say like 20. Let's make it higher for now, just for demo purposes. Make it high. So if I put 100 micron spacing, that means for every 100 micron, I have one pixel for my mapping. Then I will calculate the volume fraction for that pixel for the region or for the volume next to that pixel. And this radius here is for how big the volume is. So I can put like 300 micron as a radius. So That means we have for each pixel in the map, the map has a spacing of 100 micron. For each pixel there, we calculate a sphere which has 300 micron as the radius, or 600 micron as the diameter. So for that size sphere, what is the volume fraction of my ROI? After setting up these two parameters, that here we have a box. We have already got two boxes generated by default. One is a default computation box, one is default mapping box. It doesn't matter which one you use, so we can say using the mapping box, which is this one. I turn off the second one. The mapping box is this size. We can change the size of the mapping box just to make it smaller, so you can, okay, let's make it smaller than the original ROI, which means the calculation of the volume fraction will be only done in this box area, in this box region. And now we can do the compute scalar and the vector field. Okay, this is the progress bar. It will take a while. When this done, it will create a new image data, and that image is the map that we want for the volume fraction dispersion. So we're going to show that quickly. Okay, so this is the new map. I'm going to change that to be nearest, so we see every pixels. And so this map has pixel size, as we said, 100 micron. If you want, you can check it here. This is the size of the map, which is 37 by 37 by 58, and have the 100 micron as the pixel size or the spacing. So, I'm going to change the color map or the lookup table for this map to be something like colorful, like this one. You see now it's a map. It shows in each pixel location, like in this location, how much is the volume fraction in a sphere of a radius of 300 micron. So in that sphere, how much ROI now, it's the pore space, how much pores are in that area. So I'm going to make this, we can make this a little bit more transparent by, let's use this opacity setting. So you can see here, because it's more in the center of the pole, so it will show a larger volume fraction. And here in my mouse, here is more about the grains of the sandstone, so it has much less porosity or pore space. We can also watch this in 3D, so we can change the 3D volume fraction. The volume fraction map in 3D, we can render it in a color lookup table. And you see the total, not the total, the The volume fraction in the space is from 0 to almost 0.45, and the color represents the real volume fraction in the different locations. So that's it for this. Hope it will be helpful.